My dear friends, welcome to Rajshekar classes on applied data science with Python. This is lecture number 577. In this lecture, we will try to understand Adam. Adam is one of the most popular algorithms or optimization algorithms in the whole of the deep learning literature. This is the most popular deep learning optimizer. So the core idea behind Adams is this. If you recall our ADA delta, in ADA delta, you are storing what just try to recall ADA delta. You are storing the exponential weighted averages. We are storing the exponential weighted average of squares of gradients. This is GT squares, isn't it? We are using this to modify our learning rate through eta dash t. Just try to recall this. We are taking squares of gradients. Just say GT square, EDA t minus 1 equal to 0.05 into GT minus square, GT minus 1 whole square. We are taking the squares of the gradients and using it. That we are using in eta dash t. In addition to take squares of gradients, what if I use EDA of GT? In ADA delta, we are using GT squares, that is ADA delta. What if I use GT itself? What is the gradient? So, in addition to gradient squares like EDA in ADA delta, what if I use EDA of GT? And there is a lot of research. I will come to the research which shows that Adam is the fastest algorithm as convergence is concerned. Adam is actually adaptive. What is Adam? Adaptive moment estimation. Why it is called moment? So in statistics, mean is often referred to as first order movement, isn't it? Just try to recall in your statistics class. Yes, your mean often called as first order movement in statistics, and variance is often referred to as second order movement. You can think of ED of GT. You can think of ED of GT as a sort of like computing mean, and when you take GT square, when you get second order movement or your variance, so that's why it is called movement estimation. You are taking the both first order movement. EDA is a sort of mean, isn't it? EDA is a sort of means. EDA of GT square is like variance, isn't it? What is EDA of GT squares? It is like variance of gradients, which is the second order movement. Let me write down the equations. First order movement is mean, second order movement is variance. So let me write down the equations. What is this equation? What it says? So the mean at time t, mt means what? Mean at time t corresponding to the first order momentum is equal to beta 1 into mean at t minus 1 plus 1 minus beta 1 into gt. Let it be equation 1. Similarly, variance at time t equal to beta 2 into vt minus 1 plus 1 minus beta 2 gt square. Let me assume this is second equation. Very simple definitions. Remember, my beta 1 is lies in between 0 and 1. Similarly, beta 2 is lies in between 0 and 1. Beta 1 is taken as, I can say, beta 1 is taken as 0.9. Typically, not always, beta 2 is taken as 0.99, isn't it? What is this? My MT, this is nothing but, my MT is nothing but what is exponential decay averages of GT, isn't it? Just try to recall that this is nothing but EDA of GT. And what about this VT? My VT is EDA of GT squares. Just see here, this is my MT. What is my MT? This is MT. MT is exponential decay averages of GT. What is this? This particular one? Variance. This is EDA of GT squares, isn't it? That is EDA of GT squares. Just let me write down the equations. What is my m cap of t equal to mt by 1 minus beta 1 power t, v cap of t equal to vt by 1 minus beta 2 power t, wt equal to wt minus 1 alpha into m dash of t by under root of v cap of t plus. This is very much like ADA delta, isn't it? It is similar to ADA delta and ADA grad. This one is like this is similar to, it's not ADA delta and ADA grad. This is similar to, this is very much like ADA delta and ADA grad, except that what is this? This one is, let me consider, yes, beta 1, just what is my equation? mt equal to, this one is my equation. If I keep beta 1 equal 0, this part will vanish, this part will become 0. 1 minus beta 1 means 1 minus 0. You will left with gt. Therefore, your mt becomes gt, isn't it? Your mt becomes gt. Therefore, I can write alpha t equal to wt equal to wt minus alpha into gt. In the place of mt, I can write gt under root of vt plus epsilon. It is just like ADA delta. It is similar to ADA delta. If I keep beta 1 equal 0, I am getting just like ADA delta, isn't it? So this is, what is this? This is called Adam. Which one is Adam? All these equations are known as, it is m cap t equal to mt by 1 minus beta 1 power t, v cap t equal to vt by 1 minus beta 2 power t, wt equal to wt minus 1 alpha into m cap of t by, this is called Adam, isn't it? So typically your alpha equal to 0.001, beta 1 equal 0.9, beta 2 equal 0.98. In standard libraries like TensorFlow and Keras, that we will see in the next chapter. These default values used extensively. Again, Adam has all the advantages that you see in ADA delta. That is converges. Just right. sorry. Adam has all the advantages that you seen in ADA delta, that is converges fast. You don't have to worry about fine tuning eta for sparse and dense features. It works. In the description section, I have added a reference link to actual research paper. This research paper is published, I think, in 2015. Adam, this research paper is Adam. I can say it's Adam research paper. I request all of you to go through this research paper. This is Adam research paper, and one of the very interesting plots in the research paper is this. This is I can say on x-axis I have iterations over entire data sets. This is your epoch, isn't it? This is your, on y-axis, this is your what is this, training cost or training error. You can think of it as training error. If you notice that the purple line that you are seeing here, you see, corresponding to Adam. This particular line is corresponding to Adam, which means I done 50 epochs. After 50 epochs, remember, on y-axis I have 0 and 10 power minus 2 and 10 power minus 1, isn't it? Just see, this one is on y-axis. What we have here, just see, this is 0, 10 power minus 2, this is 10 power minus 1, isn't it? This is the MNIST data set with dropout layer. What's happening here? The training error that you get with Adam is significantly lower than the training error that you get with ADA grad, RMS prop, GD Restro, and ADA delta. Adam, even in lots of experiments, has shown to be extremely fast and works very, very well. And my personal preference, if I have to choose an algorithm, Adam is one of the best algorithm that I choose. In next lecture, I will explain you various cases where we will where we will understand which optimization works better in which case. Thank you very much.